Unit 1, Session 3. In the Session 3, we are going to discuss on Poisson's ratio, elastic constants and their relations, and simple problems on previous sessions and also on this session. Before going to start Poisson's ratio, we will go back to the previous sessions, what and all we have studied in the previous sessions. In the session 1, we have studied introduction part of the simple stress and strain and definition of stress and formula used to find out the stress. And in the session 2, we have gone through the different types of stresses and strains, explanation related to the respective stresses and strains and their respective mathematical formulae. Now in this session, we will see what is Poisson's ratio. The Poisson's ratio is defined like this. The ratio of lateral strain to the longitudinal strain is a constant for a given material when the material is stressed within elastic limit. Remember this, when the material is stressed within elastic limit. Within elastic limit only we are defining again the Poisson's ratio is the ratio of lateral strain to the longitudinal strain, and this ratio we are going to call it as the Poisson's ratio, and it is generally denoted by a Greek letter mu or nu or 1 by m. So look at the figure. In the figure I have shown here, it is a bar material. So for the bar material, I have applied pull type of force. Whenever you apply a pull type of force, that is P, on one direction means in the direction where the load is applied, in that direction the dimension increases. So in this figure, the dimension increases along the applied force direction is L. So that is, initially the length is L. After applying the force P, the length increases to L plus delta L. If along the longitudinal direction the dimension is increases, definitely in the other direction, that means in the transverse direction, the dimensions must reduce. So I have shown that in the left hand side figure. So in the left hand side figure, so initially the dimensions are B and D. After applying this pull type of force, it reduces, B reduces to B minus delta B and D reduces to D minus delta D. So this is because there is an increase in the length. Simultaneously, the other dimensions in the transverse sections reduces. So remember, so lateral strain means this strain related to the lateral direction. Then longitudinal directions is related to the longitudinal direction. So now when I define the lateral strain is equal to, so delta D by D, that is equal to delta B by B. Now the longitudinal strain is equal to change in length to the original length, that is equal to delta L by L, delta L by L. So now we'll see what is the relation between the elastic constants. So we have studied in the previous sessions, I mean it is in the session 2, the different types of elastic constants. The Young's modulus, or it is also called as modulus of elasticity. And next we have seen the bulk modulus. Bulk modulus is denoted by K, and again we have seen there is a modulus of rigidity. So as you know, what is Young's modulus? Young's modulus is the ratio of the direct stress to the direct strain, and also the modulus of rigidity. The modulus of rigidity is G, that is the ratio of shear stress by shear strain, and the bulk modulus K, that is the ratio of direct stress to the volumetric strain. These three elastic constants definition you have seen in the session 2. Now we are writing the relations between these three elastic constants considering the Poisson's ratio. So initial relation, the first relation, the relationship between Young's modulus E and rigidity modulus G and the Poisson's ratio mu is expressed as E is equal to 2G. So inside bracket 1 plus mu. This is the relation between the Young's modulus, this is rigidity modulus, and mu is the Poisson's ratio. The relation, you should remember only the relation at this point of time. For the diploma, you have to remember only the relations between the elastic constants. You don't worry about how this equation arrived. So this explanation or derivation is not there for your syllabus. It is clearly mentioned in the syllabus. Just remember the relation between the elastic constants. This is the first relation between the elastic constants. The second one is the relations between Young's modulus E, bulk modulus K, and the Poisson's ratio mu here again. So that is given by E is equal to 3K 1 minus 2 mu. Again, the third relation is Young's modulus can be expressed in terms of bulk modulus also here K and rigidity modulus G. So now it is given by 9 kg by 3k plus g. So here look at all the three equations, this equation, and in this equation, all the three equations, it is expressed in terms of Young's modulus only. So see all the three equations, we have given E is equal to remaining elastic constants only. So now, if you don't know the Poisson's ratio, but you are knowing all the three elastic constants, if you know that, so with the help of all the three elastic constants, you can find out the Poisson's ratio, and that relation is given in the last equation, that is mu is equal to 3k minus 2g divided by 6k plus 2g. So now we will solve some of the problems on the session 1, 2 and 3. So first we will see the problem 1. What this problem is says now. A load of 5 kN is to be raised with the help of a steel wire. Find the diameter of the steel wire if the stress is not to exceed 100 megapascal. So after reading the problem carefully, read it twice, thrice, and understand properly what is given in the problem and what is asked to find out. The solution goes like this. So given data, write down clearly from the problem what is given. So in the problem you have given P is equal to 5 kilonewton. So this 5 kilonewton, writing it in Newton. So kilo is 10 to the power of 3. So it is 5000 Newton. Now he is asking you to find out the diameter. Find the diameter here. Asking the diameter. So to find D is question mark here. And he has also given the stress. So the stress is sigma 100 megapascal. In the first session, while explaining the units of stress, I have told you how to express the megapascal, kilopascal and gigapascal to Newton per mm square. So now it is given 100 megapascal is equal to 100 Newton per mm square. So now you need to find out D first. To find out D, first you have to write the equation for stress. We know that stress is given by stress sigma is equal to applied load by original cross-sectional area. Now that is sigma is equal to P by A. So P is 5000. A is not given. You need to find out A. Then sigma value is given as 100 Newton per mm square. This load is 5000 and area you have to find out from this equation. So from this I can find out to be 1000. That is how I think I have repeated this equation twice here. So coming back once again directly here, this is 100. So 5000 by A. So A is equal to, that is 5000 divided by 100, means A comes this side and 100 comes at the bottom. So it is 5000 divided by 100 is equal to 50 mm square. Area is 50 mm square. So when he has given the diameter, definitely it is a round bar. With the help of area, you can easily find out the diameter. So area is given as A is equal to pi by 4d square. So d is equal to square root 4a by pi. Substitute all the values. You knew all the values here. 4 into 50 by pi. It is 7.97 mm. Now round it off this 7.97 as diameter 8 mm. So now a tensile test is performed. So second problem now. A tensile test is performed on a brass specimen 10 mm in diameter using a gauge length of 50 mm. When applying axial tensile load of 25 kN, it was observed that the distance between gauge marks increased by 0.152 mm. Calculate modulus of elasticity of brass. So read it again in the problem twice, thrice, carefully, analyze it, understand it, what is to be given and what is he is asking. So he is asking modulus of elasticity. Modulus of elasticity is E. So now the solution. Write the given data. In the given data, so he has given P. P is equal to 25 kilonewton. Again convert kilo into the newton. It is 25,000 newton. Diameter P is given as 10 mm. And length L is given 50 mm. And delta L is also given. It is delta L. It is delta L also given 0.152 mm. It was in the problem, it was observed that the distance between the gauge marks increased by 0.152 mm. So increase by means it is the delta L. So what he is asking? He is asking to find out the stress sigma question mark and strain epsilon again is question mark, and next he is asking to find out the modulus of elasticity. So I have put the stress question mark and epsilon question mark means to find out the modulus of elasticity you need sigma and epsilon, because you know already the Young's modulus or the modulus of elasticity E is given by the ratio of stress and strain. So to find out stress, what you need to find out the stress, if sigma is equal to, it is P by A. So now find out A area is required here. So area, it is pi by 4 into d square. So that is equal to pi by 4 into 10 square is equal to 78.53 mm square is the area. So then find out the stress sigma. As you know, to find out the sigma, it is applied load by original cross-sectional area, that is equal to P by A. So P, that is load given in the problem, that is 25,000 divided by area is 78.53, just now calculated, substitute it in the formula, then you arrive the stress as 318.4 Newton per mm square. The next you find out the strain, that is epsilon. It is given by change in length to the original length. So if I write this in the formula as delta L by L it is. So now the delta L is given in the problem 0.152. divided by this is 50. So this is equal to 0.00304. There is no unit for the strain. And next, find out the Young's modulus. Young's modulus is given as sigma by epsilon. This is equal to, substitute the values of sigma and epsilon here. The sigma value is 318.4 to the 0.00304 is a strain, and you arrive the answer as 104.7 into 10 to the power of 3. Now I'll write this as 1.05 into 10 to the power of 3 Newton per mm square. So write it what he has asked in the problem. What he has been asking Young's modulus. So write it clearly at the last. Young's modulus E is equal to 1.05 into 10 to the power of 3 Newton per mm square. Newton per mm square. It is not 10 to the power of 3, it is 10 to the power of 5, and this is also 10 to the power of 5. So it is 1.05 into 10 to the power of 5 Newton per mm square. So now we'll see what is the third problem. The third problem is a rod of diameter 15 mm and 50 mm long is subjected to tensile load of 25 kilonewton. The modulus of elasticity for steel rod may be taken as 2000 kilonewton per mm square. Find stress, strain, and elongation of the bar due to applied load. Once again, read the problem carefully. So you read the problem again and again. How much times you will read the problem, it is easy for you to understand what he is asking and what is to be given data. So now in the problem third, the given data is, he has given the diameter here, diameter 15 and length 50 mm. So D is equal to 15 mm, length L is 50 mm. So the P also given load is 25 kilonewton. So P is equal to 25 kilonewton. So that is equal to 25 into 10 to the power of 3. It is Newton. So E is equal to 200 kilonewton per mm square. So I'll write it now, 200 into 10 to the power of 3 Newton per mm square. And to find is stress, strain, elongation. What is elongation? Elongation is nothing but it is deformation. He is asking the deformation. Deformation means delta L is asking. So next, now original cross-sectional area. We need to find out what is the cross-sectional area. The cross-sectional area is given by, again, A is equal to pi by 4 into D square. This is equal to pi by 4 into 15 square. Diameter is 15. So after substituting the diameter value in this area formula, it works out to be 176.7 mm square. We know that stress is given by the formula applied load by original cross-sectional area, that is P by A. So P is 25 into 10 to the power of 3 to this 176.7. So after solving this, this is equal to 141.47 Newton per mm square. So the sigma is equal to 141.47 Newton per mm square. So find out the Young's modulus now. To find out the Young's modulus, so the sigma, the Young's modulus is given by the formula sigma by epsilon because it is the ratio of stress by strain. So now I'll bring epsilon this side and E this side, right? So if I both interchange this, then this works out to be epsilon is equal to sigma by E. So epsilon is equal to 141.47 to the 200 into 10 to the power of 3. So after calculating this, we'll get 7.07 into 10 to the power of minus 4. So epsilon is equal to 7.07 into 10 to the power of minus 4. There is no unit for this, no unit. it is only 7.07 into 10 to the power of minus 4. It is unitless. And also epsilon is equal to delta L by L. You know, it is a strain formula. It is delta L by L. So again, delta L, you need to find out delta L. So for this delta L, this L multiplies with this. So it becomes delta L is equal to epsilon into L. So delta L is equal to 7.07 into 10 to the power of minus 4 into 50. So this is equal to 0.035 mm. Therefore, delta L is equal to 0.035 mm. So at the end, you need to write all three values, sigma, epsilon, and delta L. Because in the problem, he has been asked to find out the stress, strain, and deformation. At the end, you have to say him back. You have to tell him back again. So what has been asked, that has been calculated. So now at the last topic, we'll see some of the multiple choice questions what we have studied in all these three sessions. The first one is stress is A. External force, B. Internal resistive force, C. Axial force, D. Radial force. What is stress is? Stress is internal resistive force. Internal resistive force. It means the solution is B here. Stress is, as I said during the stress definition, stress is always the internal resistance set up in a material for the externally applied load or applied force. So now the stress is internal resistive force. Second, following are the basic types of stress except tensile stress, B. Compressive stress, C. Shear stress, D. is volumetric stress. Basic types of stress. While explaining the types of stress, I have not explained what you mean by volumetric stress. Volumetric stress is not the basic type of stress. Only the basic type of stress are tensile stress, compressive stress, and shear stress. So the answer is D, that is volumetric stress. Third one, when tensile stress is applied axially on a circular rod, its diameter decreases, length increases, volume decreases. When tensile stress is applied axially on a circular rod, its diameter decreases, length increases, volume decreases. Which of the above are true? Only one, only second, first and second, all of the above. As you know, when the load is applied axially, definitely the diameter decreases because length increases. When the length increases in one dimension or the one direction, the length increases, then as I said, the transverse dimension must decrease, right? The diameter decreases when there is a length increases. So if there is a decrease in the dimension, then definitely the volume also decreases. So the answer is all of the above is correct here. Fourth one, when tensile stress is applied axially on a circular rod, its diameter okay, fourth one, when tensile stress is applied axially on a circular rod, its diameter increases, length decreases, volume decreases. Which of the above are true? A only 1, B only 2, C first and 2, and D all of the above. So the solution here is C, that is 1 and 2, both 1 and 2, that is the diameter increases and length decreases. Fifth one, which of the following is not a basic type of strain? that is the compressive strain A, then B is shear strain, C is area strain, D is volume strain. Now, which is the basic type of strain? But out of four, one is not a basic type of strain, that is area strain is not basic type, because you have studied the types of stress and strains, the compressive strain, shear strain, then volumetric strain. Other than this, one more, that is the tensile strain. So the area strain is not a basic type of strain. Then the answer is C. Sixth one, tensile strain is A, increase in length by original length, decrease in length by original length, change in volume by original volume. D is all of the above. What is tensile strain? Tensile strain, when the pull type of force is applied on a material, then there is an increase in the length, right? So A is correct, that is increase in length to the original length. The solution is A here. Then seventh, compressive strain is, compressive means it is a push type of load or a force is applied on the material, then there is a decrease in the length to the original length. So the A is increase in length by original length, B is decrease in length by original length, change in volume by original volume, all of the above. One is B, that is decrease in length by original length, B in the compressive strain. Then eighth, volumetric strain is increase in length by original length, decrease in length by original length, change in volume by original volume, all of the above. When you are asking about volumetric strain, then definitely there is a change in volume by original volume gives you the volumetric strain. So that the answer is a C, that is change in volume by original volume. Ninth one, Hooke's law is applicable within A, elastic limit, B, plastic limit, C, fracture point, D, ultimate strength. As I said, or while defining Hooke's law, I told you clearly the Hooke's law applies only within elastic limit. And also we defined the stress is directly proportional to strain within elastic limit. So this is the Hooke's law. So the answer is A. Then Young's modulus of elasticity is tensile stress by tensile strain, shear stress by shear strain, tensile stress by shear strain, shear stress by tensile strain. Young's modulus, it is Young's modulus, that is Young's modulus means that is E. E is defined as it is the stress by strain. It may be a tensile stress by tensile strain, or it may be a compressive stress by compressive strain. Both holds good. But in this answer is given only one, that is A, that is tensile stress by tensile strain. The answer is A. 11th, modulus of rigidity is A, tensile stress by tensile strain, shear stress by shear strain, tensile stress by shear strain, shear stress by tensile strain. So modulus of rigidity is denoted by C, or sometimes it is G. So as we explained, so this modulus of rigidity as it is the ratio of shear stress by shear strain. Modulus of rigidity is shear stress by shear strain. The answer is B. 12th, bulk modulus of elasticity is, as you know, what is the bulk modulus? So given answers are A, tensile stress by tensile strain, B, shear stress by shear strain, C, tensile stress by shear strain, D, normal stress on each face of the cube by volumetric strain. So the answer is, it is a normal stress on each face of the cube by volumetric strain, that is D. So the answer is D. So thank you. That is the end of session 3.